Simulate the impact of mechanical designs on optical performance with LensMechanix, a SolidWorks Gold certified add-in from Zemax.
Hello and welcome to this webinar brought to you by Zemax. Today we will cover adding fold mirrors inside of LensMechanix. Fold mirrors are very useful when trying to create a product that will meet a form and space requirement. Fold mirrors are already commonly added to optical designs, but they frequently can be the source of headaches for optical and mechanical engineers that need to work together. Getting the right angle and placement of the mirror can require all involved to sit next to each other and verify the position of the fold mirror. LensMechanix has already enabled the ability for these engineers to work more efficiently and with the fold mirror tool, we're improving that even further. In this webinar, we'll demonstrate how to add a fold mirror into your system, interpret the results from the optical performance summary that will appear after adding a fold mirror. You'll see how the lights travel through the folded system with a few examples, how to add multiple fold mirrors, and some best practices to avoid any pitfalls when using the fold mirror tool. Let's quickly talk about what fold mirrors are. They're frequently flat mirrors that are used to change the path of a beam. As I mentioned earlier, they can be used to fit any optical system into a prescribed mechanical footprint. In the image shown, you can see the longitudinal space savings after adding a single fold mirror in this example system. While the system length is originally 50 millimeters, we can see that by adding a fold mirror, it reduces the overall length by almost half. This is a very simple example, however, it demonstrates the utility of a fold mirror. Alright, now that we've covered what fold mirrors are, let's see where the tool is in LensMechanix. The fold mirror tool is located in the command manager under Add Parts. In order to see the Add Fold Mirror tool option inside of LensMechanix, you first need to create a new prototype. If you try to look for the tool prior to creating a prototype, the option will not appear in the menu. After creating the prototype, we recommend that you run a baseline ray trace. With the information collected from this ray trace, LensMechanix will be able to know in what order the optical components interact with light from the source. This will give the best overall experience because some of the automatic functionality will be employed when using the fold mirror tool. Once a prototype is created, the Add Fold Mirror tool option will appear in the Add Parts submenu of the command manager. The entire function of the Fold Mirror tool is controlled by the PMP that will appear after the menu option is selected. When you see the PMP appear, the first thing to notice is the warning message. It is important to note that the undo function does not work on the fold mirrors added with this tool. Therefore, we strongly recommend that you save your assembly prior to adding a fold mirror to your system. Now, with the warning message out of the way, the next session covers references. LensMechanix needs some information to know where to place the fold mirror. Select the first two references that you would like to place a fold mirror between, labeled the first and second reference. Next, choose a target component. The target component serves as the indicator of the limits of what the fold mirror tool should take into account. More often than not, the target will be a detector at the end of the optical train. Once the target component has been selected, two things will occur. If you have performed a baseline ray trace prior to using the fold mirror, then a boundary box will appear and LensMechanix will automatically add all components in the optical path and the second reference between the second reference and the target component to be included in the component sections. Second, LensMechanix will generate a preview where the fold mirror is, how it's orientated, and where all included components will be placed after the fold mirror is added. So remember that there's no undo ability. However, there is a preview to help make sure the fold mirror is added in the correct orientation and position. Here's another section of the fold mirror PMP. We've already covered the included and ignored component section. You can also define the specifications for the fold mirror in the tilt section. A 45-degree angle is probably the most common. However, you can enter any arbitrary angle that you need for your system. The axis of tilt can be in X, in Y, or even in both. If you've used Optic Studio, you're familiar with fold mirrors in sequential mode. The fold mirrors that you add in LensMechanix are non-sequential. You can also select the shape and thickness of the fold mirror. You can choose between either rectangular volume or cylindrical volume. Before we get into some demonstration files, there are a couple more details about the fold mirror tool that we'll go over. First, annuli that are present in the assembly must be added manually. This is because while the baseline ray trace will add all components that are in the path, annuli by design are not inside the optical path, so they're not going to be added automatically. You can add these objects simply by clicking on them. Another thing to keep in mind is that components that are mated to included objects are going to be affected as well. If there are multiple mates that are already over-defining a mechanical component, then SOLIDWORKS may solve the problem by placing the mechanical components in unexpected locations or orientations. This would be the same experience one would have if they were to have too many conflicting mates on a mechanical component in SOLIDWORKS. Next, with regards to detectors, when you choose one detector, LensMechanix will automatically choose all other detectors in the computational domain. This is because there are instances where you have you may have a few field detectors, each of which are very small. It's rather tedious to add them all manually, so we'll let LensMechanix do the work for you. Finally, LensMechanix will keep track of the optical path length of the entire system. So if there are any changes to the position of the mirror in the PMP, then the distances will be changed automatically. Okay, let's go ahead and look at some demonstrations. Okay, LensMechanix has already loaded the example file. This is the laser source with aplunatic lens example file that ships with every installation of LensMechanix. So now that the file has been loaded, if you look at the command manager and under add parts, there would be no add fold mirror option. You first need to create a prototype. So we'll do that by clicking create prototype and then default prototype. We'll ensure that everything's inside the computational domain and click OK. Next, we're going to add a fold mirror between object 9 and object 13. I'll first run a baseline ray trace in order to utilize the automatic tools inside the fold mirror tool. With that ray trace done, we're now ready to add the fold mirror. We'll go to the command manager, and under add parts, you'll now see the add fold mirror option. When the PMP appears, we'll see that we can choose our first reference, but also make sure to remember the note that we should have saved an assembly prior to using this feature. So you can always click out, press the cancel and save the assembly. However, I'm confident in where we're going to place the fold mirror here. So I'll first click the object 9, then I'll click object 13. Next, I'll click the target component. In this case, it will be the detector. So now you'll notice that I clicked one detector and it automatically added the color detector and object 14 because we had already run a baseline ray trace. We'll also see the preview appear. In this case, the mirror is perpendicular to the optical train, so it's reflecting back upon itself. So now we'll add a tilt for the fold mirror. We'll input a 45-degree angle, and we'll notice that the preview updates. Before we click OK, there's a couple things we're going to change. First, remember that annuli are not added automatically. So let's go ahead and zoom in on the system, and notice we have a few of them that we need to add. And it simply just takes clicking on them to add them to the included components section. Once that's done, I want to actually have the fold mirror a little bit closer to the first reference. So I'm going to go ahead up here and change the distance from its automatic input to 50.8 or 2 inches. And for the size, I'm just going to make it 12.7. And then I'll click OK. So now you can see that the fold mirror has been added. We'll go ahead and do a baseline and a full ray trace. Okay, with the ray traces done, we can go ahead and click the green check mark and see that the ray trace has updated to include the custom fold mirror. In the optics manager, it appears here as object number 17. What we're going to do now is add a second fold mirror to sort of make a two mirror alignment system that you would commonly see on a optics workbench. So we'll go ahead and click add parts and add fold mirror. This time for the first reference, we'll choose the initial fold mirror, and the second reference will again use object 13. For the target component, again we'll choose the detectors. Make sure to add the annuli to the system. Then we're going to want a 45-degree mirror here. And I want to flip it because I want it to point the other way. And we'll make some adjustments here. Okay, so now we have a two mirror system. We have our preview updated, and we'll go ahead and click OK. Once that's done, we want to see how the updated ray trace performs. So let's go ahead and run another baseline and full ray trace. Okay, with the second ray trace complete, we can see that our optical train has been modified to include our two references. What I like about this example is that it has the annuli, which will verify that our performance is the same after adding fold mirrors as it was before. Therefore, we've maintained the alignment throughout the system. Now let's check the optical performance summary, or OPS. Looking at the OPS, we can see that we have green in spot size, we have green in image contamination, meaning we haven't changed anything above the allowable delta. However, if we look at beam clipping, we have 10% beam clipping. Almost 11%. This is in fact due to adding those fold mirrors. The fold mirrors are non-perfect, non-ideal mirrors, so they lose a little bit of power with every fold mirror that you hit. You can approximate it to about 5% per fold mirror. Now, say you were to have a number of mechanical components and a few fold mirrors, then it's possible that the beam clipping calculation would include both beam clipping caused by fold mirrors and by mechanical components. So in order to isolate just the beam clipping that is caused by mechanical components, you can actually add an ideal mirror surface or coating to the custom fold mirrors. To do that, just right-click one of the custom fold mirrors and click Edit Optical Properties. In the first tab of the Lens Data PMP, it's going to have the material and type of object with the parameters. We're going to focus instead on the Coding Settings tab. In the Coding profile, click Ideal Mirror, and then click Apply to Component. We'll do the same thing for the second mirror. Once the ideal mirror coating has been applied to both fold mirrors, go ahead and run another full and baseline ray trace. Okay, with the ray trace complete, we can see OPS and see that the beam clipping issue has been resolved. So now there's less than 1% beam clipping caused by the fold mirrors, and that indicates that the improvement due to adding the ideal mirror coating. Okay, now we're going to take a look at a different example that employs a few more sources. Okay, with the second example loaded, this example is a rather simple optical system. It just has two objectives. However, these fields are distributed in a two-dimensional array. So we have a more complex problem when dealing with a fold mirror. Our previous example just had a single on-axis source. That problem is complicated when you do off-axis sources in X or in Y independently. However, in this case, we have our sources and field detectors distributed in X and Y. So adding fold mirrors uh, creates a challenge in order to place them properly. So to see how it works, let's go ahead and create another default prototype. We can go ahead and run a baseline ray trace. Baseline ray trace is done. Let's go ahead and add a fold mirror. So for the first reference, we'll choose the first lens object. And for the second, we'll choose this object here. And I'll adjust the distance again from the first reference. I'll put 100. And for a target component, I'll choose the color detector. And now we'll see that LensMechanix is adding not only the color detector, but all field detectors as well. And because we ran a baseline ray trace, it'll add the other object, lens object. We could add a 45-degree tilt to this mirror. Let's go ahead and do something a little bit different. Let's do a 31-degree in X and a 27-degree in Y. We'll go ahead and change the radius to 40 and make this a rectangular volume. Then we'll click OK. We can go ahead and run a full ray trace. We'll go ahead and check baseline ray trace as well and see how the light goes through the fold mirror. Okay, with the ray animation, we can see how light travels through the system now. Let's go ahead and add a second fold mirror, just like we did before. We'll choose the first fold mirror as our first reference, the second fold mirror as our the second lens object as our second reference. We'll go ahead and choose the detectors as our target component. Okay, and let's go ahead and add some angle here. So we'll go ahead and do 35 in X and maybe 35 in Y. And we can just flip and make whatever system we want. That looks good to me. So again, we'll keep this one a circle, cylindrical, and we'll change it to 40 once again, and click OK. So now let's go ahead and run a baseline and full ray trace. Okay, with the second ray trace complete, we'll once again do the ray animation to see how the path rays go through the optical system with the two fold mirrors. And we can see that everything meets up at the detector plane as expected. Now if we look at the OPS, we'll again see beam clipping as expected, but what I'm more interested to see is the spot size. I want to demonstrate, in order to demonstrate how the detectors are matched up properly, we'll go ahead and look at the spot size diagrams. In this case, we have 9 field detectors, and let's go ahead and cycle through. You'll see that the spot size is maintained for all 9 field points. It just shows the complexity at which you can design systems with the fold mirror tool inside of LensMechanix. We're excited to offer this new feature in LensMechanix. It will be released in the next version of LensMechanix 4.5. We're excited to see what our customers can do with it. So that concludes today's demo. Please submit any questions via the GoToWebinar control panel. And if we don't get to your questions today, or you have other questions in the future, please send us an email at lmxsupport@zemax.com. Thank you and have a nice day.
Can you save an ideal mirror as a default? So I'm understanding that means that when you add an fold mirror, can it be ideal by default? Well, that is something that we can definitely look into doing. We consciously chose to not keep it ideal because here we like to sort of err on the side of caution. We don't want to give too much optimistic results. So some power loss would be seen in real life. So just to keep that in mind, we decided to keep it non-ideal. So it is an aluminum mirror, which would be something you see in with the fold mirror tool anyway in Optic Studio. But making it ideal by default might lead some people to think that their system is performing a certain way, and once they create it in real life, they might be disappointed with the results. So that's why we went with aluminum mirror. Why does undo not work? Yeah, this so when we were designing the feature, found that there is a slight bug in the SolidWorks API. It does not allow for undo with this sort of components that we're adding. So in order to provide the feature now, we decided to just um, provide it and give as much warning as possible. That way folks can use it and we can develop it. Otherwise, we have to wait for a different company to correct an issue. And, we don't have control over that. When is it going to release? So LensMechanix 4.5 is slated to release in a couple of weeks. We're finishing up testing and making sure we have all of our ducks in a row before we release it to the public. Oh, this is a good question about coatings. Yes, so if you wanted to, and I mean, we have to figure, there'd be some manual movement to do this, but if you added a fold mirror and you wanted to make it a ideal splitter, so if you're doing like a beam splitter, that's definitely possible to do with LensMechanix. You just, instead of using the ideal mirror coating, you would just use the ideal splitter. That also is shipped with LensMechanix. Will the fold mirror capability be added to LensMechanix for Creo beta version? So for Creo beta version, not entirely sure. The beta version is not going to be feature complete, from what I understand. We're aiming to have most of the features of LensMechanix inside of the beta, but we won't have everything, just because of scheduling. In order to get the beta out sooner rather than later. I mean, if we wait till we have all the features, then we might as well just release the software. We do intend to have a feature equivalent version of LensMechanix for Creo. So any feature you use in LensMechanix on SolidWorks, you'll be able to use it in the LensMechanix for Creo. The UI inherently will be different because it's going to be different CAD packages, but overall, you should be able to do the same features. Oh, are you adding the capability to remove fold mirrors similar to Optic Studio? So that might be something we actually eventually add, especially if we don't really get any feedback regarding the bug in the API from SolidWorks. It might be something that we can do to sort of alleviate the pain between using not being able to undo a feature, which is really can it's something we take for granted. But we're actually going to wait to hear back from users, and with the feedback that we get from folks, that's what we're going to decide to how to move the feature forward. So if there's something that you like or you don't like, especially, please let us know. That's what we're waiting for, and that's with not only the fold mirror tool, but all other features of LensMechanix. We do really care about the feedback we get from customers, and that really does help drive where we're going with the software. Can I adjust the flatness of a mirror? So this one is a good question too. Good questions today. So right now the flatness is going to be the default cylindrical surface mirror. That is something though that we were thinking of. We didn't add it now just because we wanted to get the first version out and iterate later on. But there are some ideas that we've had to maybe have a flatness selection or a reflectivity selection, because you have like the silver plated mirrors, aluminum plated mirrors, or gold plated mirrors, and be able to choose that. So it might be something that we eventually add. Just make sure to, I'm writing it down now, but if you find out that you're using it and you really want that feature, send us an email and we'll make sure to put it in our feature requests, and that way it stays on record so we can keep track when we're looking at the next thing to add. We'll go ahead and end the webinar.